Hello, and welcome to MiniLecture 10 on divergent limits and limits at infinity. So we touched on divergent limits in the last lecture, where the limit evaluates out to being plus or minus infinity, or diverges to plus or minus infinity, and hence does not exist. And we also talked about how to evaluate the limits of some functions using limit rules. In this lecture, we'll go back and we'll review divergent limits, and we'll also talk about the case where you're taking the limit as the independent variable goes closer to positive infinity or to minus infinity. All right, so first of all, some review of divergent limits. A limit is divergent and is said to not exist. It's called divergent and is said to not exist if it approaches plus or minus infinity. Examples of this include the limit as x goes to 0 of logarithms. So in the last lecture, we used the natural log of x. In this lecture, though, let's consider the log base 10. The same things apply. We cannot actually ever get to 0 because the domain of a logarithm is the strictly positive numbers. But what happens as we get closer and closer to 0? Well, we approach a vertical asymptote at 0. And the limit as x goes to 0 of the log of x approaches minus infinity. All right. An alternative example of this is the function 1 over the square root of x as we approach the value of 1. And now this has a different left and right limit. As we approach it from the left, it diverges to positive infinity. As we approach it from the right, it diverges to negative infinity. And the result is a vertical asymptote at x equals 1. So the limit as x goes to 1 from the right-hand side is equal to minus infinity of f of x. And the limit as x goes to 1 from the left-hand side of f of x is equal to positive infinity. And we have, therefore, a divergent limit, and the limit does not exist. All right. We can also take the limit as the independent variable gets closer to infinity. So if we take the limit as the independent variable, the variable on the x-axis goes to plus or minus infinity, then this results in a horizontal asymptote. For example, we have a horizontal asymptote here. So the function gets closer and closer to this value, but never crosses or touches this line. We can take the limit as the independent variable goes to infinity for both continuous functions where you don't have to pick up your pen and discrete functions where you do have to pick up your pen. So note for this function over here, we're considering the domain of the function as the positive integer. So n has to be a positive integer, and we can take the limit as n goes to infinity. All right. So we will come back to these two examples to figure out what these two horizontal asymptotes are by taking the limit. But for now, let's just put that in our hat that they do approach a horizontal asymptote. All right. So what does it mean to take the limit as the independent variable approaches infinity? Well, it tells us biologically the long-term outcome of the system. So for example, in the logistic growth model, so this is a model of population growth with competition, individuals start competing with each other more and more as the population size gets large, and we end up reaching a horizontal asymptote at the carrying capacity of the system. The carrying capacity tells us the long-term dynamics and the amount of individuals a particular environment can hold. Similarly, if we talk about the long-term behavior of exponential population growth, as time goes to infinity, exponential population growth flies off to infinity. This is a divergent limit. And this means that the system is actually not biological. So exponential population growth does not have biological long-term dynamics. It is a good model of dynamics in the short term, of rapid growth in the short term, but as we go to the long term, we end up flying off to infinity. So this is not a biological model. In the long term. So a model doesn't always have to work for all possible values of the independent variable, and in this case, an exponential growth model is used very often when t is small, but as t gets to infinity and we end up approaching the long-term dynamics, then it is no longer reasonable. All right, so we've talked about lots of different biological functions in this class, in particular polynomials, exponentials, and logarithms. So let's talk about what happens as we approach infinity for these types of curves. All right, so first let's talk about a quadratic. Here I show two different quadratics, one where the leading term is positive and one where the leading term is negative. In the case of the positive one, as we approach t is equal to infinity, we will end up diverging to positive infinity, and as we approach t equals minus infinity, we'll end up diverging to minus infinity. Similarly, as we take t goes to infinity, but where the leading term is negative, now this term is going to get bigger and bigger and bigger, but it's going to be negative. So if it's negative and it's squared, so we have negative infinity essentially squared. This is a huge number, and then you're multiplying it by a negative sign, and so you're going to diverge out to minus infinity. Similarly, if you have positive infinity, you're going to have positive infinity squared. Now, we can't actually square positive infinity, but it's kind of a useful thing to think about in your mind to understand what's happening. If we have positive infinity squared, that's a huge number, and then we're still multiplying it by a negative sign, and we're going to diverge to minus infinity. All right. Similarly, if we do a cubic, we have, if this leading term is positive, we have positive infinity cubed. That's a positive times a positive times a positive, which is going to come out to being positive infinity. But if we plug in minus infinity cubed, that's a minus infinity times a minus infinity times a minus infinity, and the net result is going to be minus infinity. All right, so we're going to diverge to minus infinity. Take a moment to think about this case where you have a leading negative cubic term to understand that this diverges to positive infinity as we go to minus infinity, and diverges to minus infinity as we take the limit as t goes to positive infinity. All right, so just like we can take the limit of polynomials, we can also take the limit of their ratios, so 1 over x squared. In this case, as we approach 0, the limit of 1 over x squared as x goes to 0. Now we can't divide by 0, so this is going to be a divergent limit with a vertical asymptote. And as we get closer and closer to 0, the limit is going to diverge off to does not exist, but it diverges to positive infinity. Similarly, if we have 1 over x cubed, this is going to be a divergent limit as 0 since you can't divide by 0, and you end up with a vertical asymptote. However, because there's a cubed, it's going to matter whether the quantity is positive or negative, so you're either going to diverge off to positive infinity, or you're going to diverge off to negative infinity, and this results in a vertical asymptote. All right, so now we've talked about limits of polynomials. How do we actually evaluate the quantities of limits of polynomials as we take the limit as the independent variable goes to infinity? Well, the key point, as you might have noticed up here, is all that matters is the largest terms. So if we're taking the largest terms that are infinity and squaring them or cubing them, whatever is the highest degree term is going to overwhelm all of the other terms. So taking the limit of ratios of polynomials is really fun as x goes to infinity. And note, the important thing here is that it's only for the cases where we're evaluating it as the independent variable goes to infinity. So this doesn't work if we're going towards 0, but it works if we're going toward infinity. Okay, so if we're taking the limit as we go to infinity, then we can cancel all but the largest terms, because the smaller, lower degree terms are going to essentially be inconsequential. Okay, so what are our largest degree terms here? We have an x cubed. Everything else is inconsequential, so everything else drops out. And this just becomes x cubed. So this is the same thing as taking the limit as x goes to infinity of x cubed. We did an example like that up here. As we go to infinity of x cubed, we're going to fly off to positive infinity. So this approaches positive infinity. Similarly, as we go to limit as x approaches minus infinity, we're going to diverge off to minus infinity, just like the cubic function here. All right. But this only works when we have a limit at infinity. So just to remind ourselves, if we're taking the limit as x goes to infinity of a ratio of polynomials, then only the largest degree terms matter. What is our largest degree term here? Well, we have a cubed, and a cube, there's nothing higher than cubed, so all of the other terms drop out, and this is the same thing as saying the limit as x goes to infinity of 5x cubed divided by 3x cubed. Now the nice thing about this is suddenly we can cancel. We can cancel that x cubed with that x cubed, and we end up with 5/3, and so our horizontal asymptote is 5/3. All right, so let's go back up to those limits that we had on the previous section where we said that we would come back to them once we knew how to take the limits as the independent variable goes to infinity. So what is our highest power in this term here, or in this ratio here? Well, the highest power is a squared and everything else drops out. So this is the same thing as saying we take the limit as t goes to infinity of 1 over 4t squared. All right, so what happens is we take the limit as t goes to infinity. We have 1 over 4t squared. So this is kind of like saying we can't actually, this isn't formal math, but kind of hand-wavily, we're saying we have 1 over infinity squared, which becomes 1 over a very, very, very large number, which approaches 0. So the fact is that we wrote our horizontal asymptote in the wrong spot here. We actually approach 0 as t goes to a very large number. Similarly, if we take the limit of 2n over 5 plus n, then we have that only the largest quantities, largest degrees matter, which here is n to the 1, so we can drop everything else. So this is the same as taking the limit as n goes to infinity of 2n over n. Now the n's cancel, and this is going to converge to 2. And sure enough, our horizontal asymptote is around 2. All right. So now we've talked about divergent limits of polynomials. What about limits of exponentials? Well, an exponential is really nice. If we have e to the at, then this is going to diverge to positive infinity if a is greater than 0. This is exponential growth. We keep getting bigger and bigger and bigger. If a is negative, however, this is exponential decay. So this is decay down here, and this is going to decay to a value of 0 until the population is extinct, or it's going to diverge to positive infinity. So it depends on the value of that a. If a is greater than 0, then we go to infinity. If a is less than 0, we go to 0. This same behavior applies to other exponential functions that have different bases. For example, base 2, you can get a different, you either diverge to infinity or you diverge to, or converge to 0. If we take the limit of 2 raised to the 1 over n, then this becomes a value of 1, because as n goes to infinity, then we have that 1 over n approaches 0, and 2 to the 0th, anything to the 0th is equal to 1. All right, so with that, I'll leave you with the self-study question.